For centuries, astronomers have observed the sun from a single, sideways perspective. Earth, along with all the other planets, orbits our star within a flat geometric disk known as the ecliptic plane. Trapped within this flat alignment, we can study the solar equator in high detail, but the extreme northern and southern latitudes remain completely out of view. Those obscured polar regions house the magnetic machinery that dictates the sun's 11-year cycle of rising and falling activity. Without the ability to observe the poles directly, our capacity to predict violent space weather events that strike Earth's atmosphere remains severely limited. The solar cycle is dictated by a massive, dynamic web of magnetic fields that structures every inch of the sun's outer layers. Every 11 years, the entire web destabilizes as the north and south magnetic poles completely reverse their polarities. The stress of this impending reversal causes magnetic field lines to twist, cross, and eventually snap, violently launching massive plumes of plasma and radiation outward. When these massive solar storms slam into Earth, they can damage satellites, endanger astronauts, and severely disrupt our power grids. To map this magnetic engine, the European Space Agency engineered the Solar Orbiter, a spacecraft built specifically to break out of our flat vantage point. Securing advanced warning of these outbursts requires a physical journey out of the planetary plane and into uncharted orbital territory. In February 2020, Solar Orbiter launched from Cape Canaveral to begin its journey toward the inner solar system. Firing a rocket directly up and out of the solar system's plane requires vastly more energy than any existing launch vehicle can provide. Instead, engineers rely on resonance orbits, a carefully calculated series of gravitational assists designed to mechanically warp the probe's trajectory over time. This chart plots the spacecraft's heliographic latitude, demonstrating how repeated flybys of Venus systematically crank its orbital inclination higher and higher over several years. Surviving this trajectory demands extreme thermal engineering, including a custom black heat shield designed to withstand temperatures of 500 degrees Celsius as the probe swings inside the orbit of Mercury. Enduring this intense heat over a multi-year orbital ballet provides the only practical method to secure a top-down view of the sun. To map the mechanisms behind solar storms, the spacecraft carries 10 distinct scientific instruments designed to operate in tandem. This extreme ultraviolet image of a solar flare was captured by one of the probe's 6 remote sensing instruments, which visually map the corona and surface features. Complementing these cameras are 4 in-situ instruments that act like physical weather stations, measuring the particles and magnetic fields immediately surrounding the spacecraft. By combining these 2 datasets, researchers can watch a solar eruption visually and then physically measure the specific particles sweeping past the probe a few days later. Connecting the visual trigger at the sun to the physical arrival of the storm yields a complete profile of how space weather travels through the solar system. By June 2025, Solar Orbiter reached a critical geometric milestone, tilting its orbit between 15 and 17 degrees below the solar equator. This angle successfully cleared the equatorial bulge, delivering humanity's first direct high-resolution visual measurements of the sun's south pole. Data revealed a highly turbulent and chaotic magnetic field, violently churning rather than behaving as a stable, unified pole. Observational. Right up to the edge of the pole, instruments detected scattered patches of both north and south magnetic polarities mixed together just before the 11-year flip. Furthermore, supergranulation tracking proved that these magnetic fields are drifting towards the poles at speeds of 10 to 20 meters per second. These turbulent flows force astrophysicists to update their models of how the solar magnetic dynamo prepares for its cyclical polarity reversal. The 2025 observations represent an intermediate step in the probe's ongoing mission. Over the next several years, the spacecraft will execute additional Venus flybys to push its trajectory to a 33-degree angle by 2029. This extreme altitude grants astronomers a complete top-down perspective to map the polar regions without any equatorial visual distortion. Back on Earth, global mission control teams will coordinate the downloading and processing of this incoming telemetry. By charting the magnetic flows at the poles, Solar Orbiter is exposing the mechanical forces that dictate the space environment for our entire solar system.